start our morning session. Marco here. It's a pleasure to present Antonio Teruel from the Universidad de las Islas Baleares. Here we speak about slow passages through a homoclinic bifurcation by piecewise linear differential system.
Thank you. Thank you to the organizer for giving me the opportunity to give. I think that I don't need this. Not that my voice working on. I want to give the thanks to the organizer for giving me the opportunity to be involved in this very nice celebration. It's for me a pleasure to contribute to this celebration with this talk entitled Slow Passage to a Homoclinic Bifurcation by Piecewise Linear Differential System. It's part of a research paper in collaboration with Jordi Penalba, MAT80, and Dynamical. The idea of my talk is try to convince you that piecewise linear system is not only have a risk dynamic node, the dynamic of the piecewise linear system is equivalent to that of the non-linear ones, but also a piecewise linear system can be used to a better understanding of non-linear dynamics, as we can see along this talk. In particular, this is true in the slow-fast dynamics, where the piecewise linear framework presents an advantage. They are the existence of canonical slow manifolds, which are easily computable and are linear manifolds. And this represents an advantage in this framework. In this talk, we will deal with the slow passage phenomena, and even when I think that most of you are aware about this topic, I will introduce a little bit. Assume that we have a differential equation, a one-parameter differential equation, and now we put dynamics to the parameter, the slow dynamics to the parameter. This, the new system, becomes a slow-fast system where variable x is now the fast variable and the parameter, which is now a variable, is the slow variable. Under this point of view, the original system is a fast subsystem that is for epsilon equals 0, and the idea is try to understand the behavior of the global flow from that of the flow of the fast subsystem. For instance, assume that the original system has an equilibrium, an hyperbolic equilibrium, and then the fast subsystems present a critical manifold of equilibrium. If the equilibrium is hyperbolic, the critical manifold is a normally hyperbolic critical manifold, and if the equilibrium is attractive, so that the critical manifold is also attractive. So under the Fenichel theory, after perturbation of this equation, the critical manifold perturbs into a slow manifold, which is also attractive. And then the behavior around this manifold is easy to follow. So this situation, the behavior around the slow manifold, the behavior of the flow in this situation can be deduced from that of the fast subsystem. But this is because all the points in the critical manifold are normally hyperbolic. What happens when this condition not happens? If there exists a point in the critical manifold at which the normal hyperbolicity is closed. For instance, when this happens, the Fenichel theory does not work, so unpredictable phenomenon can happen. Imagine, for instance, that we have a critical manifold and a point in the critical manifold at which the system loses the stability. There are a change of stability in this critical point, in this equilibrium point. So the critical manifold is split into two branches, one which is stable and the other which is unstable. And in this condition, when we perturb this situation, typically both branches of the critical manifold perturb into a slow manifold. Typically, this slow manifold does not connect, and the flows surrounding these manifolds present a delay in the loss of stability, because for a time the flow follows the repelling branch of the slow manifold, the repelling slow manifold for a while. So appears a delay in the loss of stability. This delay is analyzed through what is known the Y-in, Y-out function, which can be understood as considering a tubular neighborhood surrounding the slow manifold and try to relate the point at which the flow go inside to the tubular neighborhood with the point at which the flow leaves the tubular neighborhood. This function, the graph of this function is typically asymptotic to a value, and this value is known as the maximal delay. The maximal delay is related with the point at which the attracting branch of the slow manifold leaves the neighborhood. Imagine that as far as you are moving on the left, all orbits collapse to the slow manifold, to the attracting the slow manifold, so the point to leave in the neighborhood is exactly at the maximal delay. So the slow passage phenomenon in this kind of bifurcation, where the equilibrium loses stability, it can be summarized in this way. The maximal delay, when assume now that we have a parameter that can control the relative position of this manifold, assuming this parameter controls the position of this manifold, the slow passage phenomenon can be summarized as this. There are different behavior for this value, for the maximal delay. One behavior is the trivial one, which is that as epsilon tends to 0, the maximal delay also tends to 0. This is natural, but because as you are tending epsilon to 0, the flow, here appears the bifurcation and the delay reduced to 0. The maximal delay also reduced to 0. So this is the trivial behavior. But there exists another behavior which is for a singular value of the parameter at which both manifolds coincide. In this case, the maximal delay is unbounded because the point of leaving the neighborhood of the attracting the slow manifold tends to infinity, so in this case it's unbounded. But surprisingly, there exists a transitory behavior between these two scenarios, which is that the maximal delay tends to a constant. This is related to the canal behavior appearing in this setting, and happens when the parameter controlling the position of the manifold are exponentially close to the value of the singular value at which coincides. In this moment, the leaving point of the attracting slow manifold can be set at the value that we want. So this is a resume about the slow passage phenomena through a point, through a bifurcation at which equilibrium point lose stability. And this can be also seen in this diagram. This scenario has been analyzed in two different situations. For instance, in the transcritical bifurcation by using piecewise linear system. This both scenario has been analyzed by using piecewise linear system. For instance, the transcritical scenario at which there exists a point where the critical manifold loses normal hyperbolicity, which is the critical point, and here appears the delay, a graph of the delay at the maximal delay. In this scenario has been observed this phenomena, and also in the Hopf bifurcation, which is a very known scenario, the Hopf bifurcation and the slow passes through the Hopf bifurcation, where the critical manifold, the attracting and the repelling manifold, here we have the Hopf bifurcation, and after perturbation appear a delay in the loss of the stability. This scenario is related with the elliptic bursting, and also it has been also analyzed by using piecewise linear system. Okay, so these are the slow passage related to a kind of bifurcation, which is, as we commented before, which is a bifurcation at which the equilibrium loses stability. But what happened in another scenario, in a non-local scenario, because here the bifurcation takes place locally. This is the case of the homoclinic bifurcation. Assume now that our fast subsystem presents a critical manifold. In this case, the critical manifold is formed by a hyperbolic saddle. So the critical manifold is a normally hyperbolic critical manifold, and in some moment there exists a homoclinic connection in there exists a bifurcation, a point at which there exists a homoclinic connection. The existence of the limit cycle on one side of the homoclinic cycle is not necessary for the analysis of the homoclinic bifurcation, the slow passage. But it is usual because this kind of behavior is very, very related with the square wave bursting. In fact, a lot of papers using square wave bursting at the end, this phenomenon is key in this kind of scenario. So I put here the systems of the limit cycles. So in this case, we have the critical manifold formed by saddles, by hyperbolic saddle. This saddle has the stable manifold and the unstable manifold, and this form a surface, and in this surface appear the homoclinic connection. So after perturbing, when we put velocity to the parameter, so the critical manifold becomes reduced into a slow manifold. The stable manifold of the slow manifold and the stable manifold, in the case epsilon 0, that is in the fast subsystem, we have a homoclinic, but what happens when the velocity, when appears the velocity in the parameter? So the idea is that the slow passage phenomenon related to this scenario consists in the existence of finitely many connections between both manifolds. This finitely many tends to infinity as epsilon tends to 0, and any of these connections has the ability of percent K turns around in this case, remember that here we have an equilibrium, a repelling critical manifold. So any of these connections give K turns around this slow manifold. In this in this form, I have not seen this in any of these articles, even when these articles are related to this phenomena, but in this case they are interested in the square wave burst. But in my opinion, this is what we can state as the slow passage phenomenon through a homoclinic connection, is that from the homoclinic connection perturds infinitely many of connections between the manifolds. And this is what we are interested in proving by using piecewise linear system. As I commented, there are some papers of Dr. Anosinga and the paper of Carter where something similar is stated, but not exactly in this sense. The connection of the stable and the unstable manifolds are not exactly stated. So this is the scenario that we want to prove. To prove that as we put velocity to the parameter and we cross the homoclinic connection, finitely many of connections appear. Of course, we have far from this result. We are not obtaining, but here we will present the state of the art. So to do that, let me to introduce this system. This system is we have called it a piecewise linear version of a neuronal model, which is the Morris-Lecard. It's a very well-known model in the neuroscience community, and it is formed when the parameter epsilon is small. This is a slow fast system, and this slow fast system, the nucline of the fast subsystem of the nucline of the fast variable, the fast nucline, is formed by a cubic shape nucline, and the nucline of the slow variable is, or the slow nucline is a sigmoid nucline. Notice that in this is also true for the Morris-Lecard neuronal model, where the slow nucline is a sigmoid, but sigmoid, and also the fast nucline is also a two function for sure. And we have just tried to mimic this with this code. The idea of putting here to mimic the fold with a three segment to mimic the fold is just in order to obtain canal dynamics around this fold. This is something that we have learned about our previous work, that in order to mimic with piecewise linear systems, to mimic the transition through the fold, we need to put here a new segment. This new segment is a kind of blowout, and this is because the amplitude of this segment is square root of epsilon, because it's a kind of locus of the blowout. Also, as it is needed that in this part, in this locus, there are no possibility, because it's the region where the Fenician manifolds are not defined. So we need to consider in this region that there are not a splitting between the slow and fast dynamics. So we consider for this part, for the part of this region, we consider trace. We consider complex dynamics here. Dynamics as focus or center or something like that. So this parameter here, using this parameter for the system, the linear system here, and this amplitude, this is what we use in order to provide a canal dynamics in this region. But unfortunately, this is not necessary for the setting of the homoclinic behavior, because what is interesting is that these other parameters of the system is just for the continuity of the model. This is not a problem. These other parameters, the K and L parameters, is just to assure that this equilibria to be a saddle and this other equilibria to be a node or a fork, but a repellor node or fork. This other equilibria is always an attractor node. So with this scenario, only three parameters remain, which are the Y, the epsilon, and the I. I is in the Morris-Descartes model, the I is the injected current to the neutron. So this is a parameter. And as you notice, the parameter I, the parameter I is related to the one of the endpoints at which the sigmoid has the linear part. No? This is A, the point A. In the neural model, in the case of the Morris-Descartes, this is related to the high threshold dynamics or low threshold dynamic that is related also with the excitability of type 1 or type 2 excitability. These are related, these are things about the neuroscience, but we consider this model because we are also interested in making a version, a piecewise linear version of the Morris-Descartes. But all these things are not necessary because we only need to understand what happens around this point and the connection, the homogeneous behavior having occurring at this point. So these are the main parameters. Notice that the parameter Y is just a translation, moving the parameter is just a translation of this nuclei. So this parameter is the one that allows for the saddle node of equilibria when we increase the parameter Y to obtain a saddle node of these two equilibria or a saddle node here of these two other equilibria. Okay, so using this system, we present the following results. So first we set the set of parameters at which we will work. It's a subset of R3. And inside of this set of parameters, we consider the set R3. And the first lemma is that when the parameters are in this set, the system presents exactly three equilibria. As I commented, one attracting node, a saddle, and an attracting anti-saddle, which can be a node or also a fork. So, under this condition, we can prove the existence of a manifold inside the set P at which the system presents, when we take parameters of this manifold, the system presents a homoclinic connection to the saddle fork. Additionally, at one side of this manifold, we have a stable limit cycle. Okay, so this is one of the results in the manuscript, and I would like to give a sketch of the proof because I think that we present some novel ideas that maybe can be used in another context. First, I notice that here, as this is the parameter A is less than 1 to obtain this central region. But when A is equal to 1, this system becomes a discontinuous system. So, in order to prove some of the things that we will do here, first we consider the discontinuous case by setting the parameter A equal to 1. So, in order to obtain a homoclinic connection to this saddle here, what we need to solve is, of course, as we are in a linear system, in this region, it is a linear system, so these are linear manifold, so it's easy to obtain these 2 points, so we just need to solve this system of 2 equations and two unknowns, which are the time of flight and which are the value of the parameter, in order to obtain this connection. This can be done easily, maybe also with the tools presented by Fernando, but it can be also in an easy way can be obtained. So we solve this problem, so that means that we obtain the homoclinic connection just in the discontinuous phase. Now, we consider the parameter less but close to 1, the parameter y less but close to 1. In this case, we have we need to solve more equations, one connecting these points, and one connecting. So we set this six equation and seven parameters, 8 parameters, no? 8 parameters. 6 equations and 8 parameters. And now what we can do is make a change of variable. Notice that the time here goes to 0 as parameter A tends to 1. So I make a change of variables to the times and also with the coordinates of these 2 points, and also multiplying the equations, these equations here and these equations here by this factor. This, from this we obtain an equivalent system. From this system is equivalent to the other one, and this system has as a solution that can be easily the time 0 here, the time of the homoclinic connection in the discontinuous case. So we can extract a solution from the discontinuous case, and then by applying we can compute the determinant of the Jacobian matrix, which is different from 0. And also this is the determinant of this connection. So from this we apply the implicit function theorem and we obtain the existence of the homoclinic surface. Okay? So I notice this because in some sense one can prove the existence of a, for instance, starting at this point to prove the existence of the homoclinic connection for A less than 1 is not so easy, but we can extract this from just by stretching this segment, this interval, no? By collapsing, passing to the discontinuous case, we can obtain, it's a way, in some sense, I think that can be useful to prove the existence of global object just by collapsing the intermediate regions, and after that, by perturbing, you can obtain the global. So I think that this can be useful for other contexts. Okay, so now we have proved the existence of this manifold in the parameter space. So now what is interesting is that to put velocity to the parameter y, we can put velocity to the parameter y in order to grow this manifold. So we have performing a slow passage through the homoclinic connection. Okay? To do that, we consider our original system. This is the extended system where we have put velocity to the parameter, and the fast subsystem of this slow fast. This slow fast system has 2 small parameters. We consider this parameter not so small, so there are no problem. We will just work with this other small parameter. Okay, so under this scenario, the slow subsystem presents the critical manifold are formed by a 4-segment critical manifold. This this branch is the attracting branch of the critical manifold, which is formed by the node, the attracting node. Notice that here we have a change, but this is just because of the small region in the small root of the zero. Here we have the critical, the equilibria, the saddle equilibria, and here we have the repelling critical manifold. These two saddle node bifurcation here are governed by the parameter y. So y is interpolation. Okay, so this scenario, in this scenario we consider the existence of homoclidities when we move the parameter y. We pass along this homoclidic orbital we have proved before. And this scenario is typical, this geometry is typical for the analysis of the Bastille behavior. So someone knows the subject. So this is a classical geometry for the square wave Bastille. So in this case, this saddle here presents an unstable manifold and a stable manifold, which are locally planes. Okay. Okay. Notice now I will change the view of this view, so I will remind, because we are interested just in this part here. So we will represent just the saddle equilibria, these two planes corresponding to the stable and unstable manifolds of the saddle, and these two regions, which are these two planes now, which are the plane x equal y and x equal y. So after perturbation, we obtain this. This means that we have the manifold of the slow manifold of saddle type equilibrium. The unstable manifold of the saddle type equilibrium, the stable manifold of the saddle type, and this is the branch of the repelling slow manifold. What is interesting in this scenario is that both the slow manifold is a segment and it's very easy to compute. The unstable slow manifold, the unstable manifold of the slow manifold is also a plane and is easy to compute, and the stable manifold of the slow manifold is also a plane and is very easy to compute. So that we present the next result, the main result of this talk, which is that under some conditions we can obtain a connection between, which is the green one, between the two manifolds, the attracting and the repelling slow, the stable and the unstable slow manifolds, stable and unstable manifold of the slow manifold. We obtain a connection between them, but without making a turn around the repelling slow manifold. And we also prove the existence of a connection giving a turn around this other manifold. In this context, to obtain this kind of orbit is just to perform the equations that giving this connection is a set of equations, because these planes are very easy to know, and also these intersections are easy to know. Let me to give you again a view sketch of the two. Again, we consider, in order to obtain the one spike orbit, we consider this continuous case. So this region collapse, these two regions collapse, and we just are in this scenario. So we need to connect this orbit to this plane with this other plane. And this is given, as this is easy to know, this point only needs one variable, this point only contains one unknown. So we can, these three equations, this set of three equations with one, but with the four unknowns, which are the four unknowns and the y value for this point to this other point, the time and the sigma. So we can solve this problem. Why? Because at the sigma equals zero, and these are the position of the homoclinic connection, and this is the time of the homoclinic connection. This is a solution of the problem. So using the determinant of the Jacobian and using the implicit function theorem, we can extend this solution, the homoclinic solution, to a connection in this one solution. Again, from this scenario, and after passing to the continuous one, of course, again appears now new set of equations, and we can, by changing variables and multiplying again, in some sense, in a similar sense as in the other case, multiplying some equation by this factor, we can obtain an equivalent system of equations that whose solution, we obtain a solution which is the one of the discontinuous. This will be a solution for an initial solution for this other set of equations. So by using the implicit function theorem, we obtain the system of a connection between these two. Just, I don't want to repeat again the arguments, but the case of the two of these terms is almost similar. So first we consider the discontinuous case, we present the set of equations and solve the problem in this case. Notice that to solve this problem is not so easy because we are starting, we want to obtain this solution, the existence of this connection, from the one of gamma 0, from the homoclinic loop. Okay, but this is a little bit difficult because we need here we have to a time which is tending to infinity when this part of the so we have to perform a different change of variables, and we have to multiply this equation by different factors. So we have to make a not very difficult, but we have to a more elaborate computation in order to obtain an equivalent system to that. But we are able to obtain the one loop or the two spikes orbit from that of the homoclinic orbit. Then we extend the case as always to the case A minus. Okay, so with this conclude the systems. Sorry, with this I conclude the proof of the system of these two loops, and we finish at this point the work. For the future, we can continue with this technique to obtain. This is a work in progress. There are different ways to try to continue with that, because the idea is to prove the system of finitely many of this connection. So the idea is to continue, let me to go with the theorem, to 3, 4, 5. Of course, this is not realistic, no? We can do that. And maybe we are trying to obtain a kind of mechanism in order to derive one from the other or something different from this. This technique is enough to prove one or even to prove two, spike and another. but not to go far. It's very complicated to go on, but it can be done if we obtain an argument or something like that. The other idea is this one. Is try to change a little bit the model, and also to consider a corner, this kind of region here. This allows for the existence of canal behavior around this corner here. And by using arguments related to the canal behavior, and in the case of for the system with the slope parameter, when we put the velocity to the parameter, which we are in a three-dimensional scenario, techniques of the folded singularity try to obtain all these connections, which are, I think, related with the secondary canal origins in folded singularity. And this is all the things that I wanted to say. There's something.
Questions, comments? Let's thanks again the speaker. It's a pleasure to introduce next speaker, Professor Henrique Ponce from Universidade de Sevilla. He will speak about complex normal forms for the double boundary Fox.
Thank you. Well, it seems obligated to say that it's a pleasure for me to be here and to participate in this lovely celebration. I put here a picture of Marco in a walk we gave some time ago, 2009. This is in London, in Dynamical, I think. But you see Marco is in front of the Houses of Parliament. And just to say something about the Marco's influence in my life, I must say that about the Teixeira singularity, I think should be the subject of my talk, but I decided not to speak about the Teixeira singularity and to take advantage of the audience just to show you some recent results and to be criticized by so many wise people. Then we meet the Teixeira singularity in our work with Rory Cristiano, Daniel Pagano, and Luis Benadero, because we found this singularity in the analysis of electronic circuit. It was in 2016, and after that we decided to look look for a more detailed analysis, and we succeed to publish this paper. Well, I must say something about this paper. You know, sometimes you have a work and this work is not well known, not well renowned. People don't know this work. So I feel about this work like a silly child. So I will take advantage of this presentation just to say, please, read the paper. Please, quote the paper. Because, you know, it's one of the least quoted paper in my Google Scholar. It's not fair. It's not fair. So, because here we work a lot to obtain to give procedures, to obtain the normal form of the singularity, to analyze the bifurcations, splitting the study into the analysis of the equilibrium bifurcation and limit cycle bifurcation. So we speak maybe not in not the right way about a compound bifurcation and so on. Please, don't forget my petition, about this paper. And after this paper, we'll also follow with another, always finding real application of this singularity, which is, it seems important to me. Not only the theoretical results, but also showing that this, in fact, has some implications in the real world. And so, you say, a lot, always with the collaboration with Ronnie Cristiano and Daniel Pagano, maybe they are here, I suppose. Then another paper, and now this is not, I am not here, but you can see the influence of the Marcos work. And another one, I think this is the best legacy of Marcos, the students. This is a picture from Bristol in 2014. 10 years ago. 10 years ago. Well, now we start my presentation, and we will speak about work which is the natural continuation of a previous one. In 2022, we obtained some results about normal forms and return maps in the analysis of pseudo-focus points. And we concentrate our attention only in the case of a double tangency point, a double invisible tangency. Is in the terminology of the seminal paper by Cole, Gazul, and Proens, this was the PP case. And after that, we decided to explore if the normal form approach could give some insight or more, some facility for the analysis of the case of focus point, the so-called FF point in the paper of Dynamical and co-workers. So we decided to pass, to try to see if the normal form gives some insight, and as they say, as they did before, we try to use the complex setting, because in this case it seems the most natural setting for the analysis. And well, we will see that we have obtained some normal form, which is in fact the easiest normal form for computing the Lyapunov constant, and so characterizing the stability and simplicity of the origin. And well, just to illustrate the usefulness of this approach, we will work with the family of piecewise quadratic linear system with a double boundary focus at the origin. And as a final comment, we will obtain a case where by considering just a quadratic system, we see that even when you put together two weak focus, this is not okay, it's not enough. When you put together two attractive weak focus points, you can get a repulsive weak focus. This last assertion is similar to a recent result from Jauma and some co-workers here in Brazil, about that when you have systems which are globally asymptotically stable, when you put together, you can obtain a new system which is not globally stable, not stable anymore. Okay, then the idea is, as you know perfectly, normal for approach is just to remove unessential terms in order to obtain the most simple expression for the vector field, and always respecting the topological type of the singularity, and also possible periodic orbits. For that, you must do changes that always preserve the discontinuity line, and not only the discontinuity line at all, but every point of the discontinuity line. This is the idea. So I insist that this was previously studied by Tomeu Cole, Armengol, Gasol, and Rafael Coens. So in some sense, this presentation is a temerity, a kind of, audacity. Staying Armengol in the audience, the tangent Armengol. Okay, then the setting of the problem. Well, you have a vector field. We use the classical terminology, left part for the half plane with x negative, right part for the half plane with x positive, and we use the subspace minus and plus for the vector fields. Our hypothesis is that at the origin we have a equilibrium point from the both sides. So we say a double boundary equilibrium point. This is the first hypothesis. The second one is just to assure that the equilibrium in both cases is a focus, which this is a standard condition for getting a focus. And finally, the third hypothesis is just that the orbit can be concatenated in a natural way, and then you have that the origin is monodromic. It's a monodromic form. Okay. And then we can use a less heavy notation by defining the entries of the linear part, and we say, well, in the rest of the vector field, yeah, when you have only monomials degree 2 or higher in the variables. Okay, and just to fix notations, the condition on the system of focus point from both sides give us the real and imaginary part of the eigenvalues for these points, and we use this notation, sigma for the real part and omega for the imaginary part. And just to work with some definiteness, we assume that this second entry in the first row of the matrices both are negative, so we guarantee that the orbits rotate in the positive sense. And so our first preparation result is just to make a piecewise linear change in the field, just to get the Jordan canonical form. And it is important to recognize that this is a generic result. You don't need any extra hypothesis, and you get this Jordan canonical form, which would be our initial starting point. In fact, we will eliminate one parameter more by changing the time and introducing the new parameter gamma. Here. This gamma is just the quotient of real and imaginary parts in the eigenvalues, and is in some sense what we call intrinsic focal parameter, because this parameter gamma is the parameter which controls the expansion or contraction of focus. So when your orbit go around the equilibrium point, after one turn you get an expansion or contraction controlled by the exponential of 2 pi gamma. So this gamma is the intrinsic focal parameter. Some remark here is just to comment that in the work by Golga Surprenz, they use this normal Jordan canonical form, and maybe they were not aware that this can be done in a generic way. So the results they obtained in such a work were more general than probably expected by the authors. Okay, then let's go to starting from this vector field. We go to take the normal form. Well, then the first point is to use the complex setting. So we introduce the complex variable Z, and we write the vector field in this more compact form. Here, the lambda plus and minus for every side represents the eigenvalues. Now, in terms of the intrinsic focal parameter gamma, and we have a normalized frequency to 1, and this is the imaginary unit of the complex plane. And so in these Q terms, we have all the terms of degree 2 or higher coefficients in C. Well, our first and more, probably the only one result in this talk is just this theory. Because what we obtain is that we can using the changes of the normal for approach that respect every point of the discontinuity line, you get some dynamical form, this normal form, NF, which had these powers on this C bar, C conjugate, and without any extra terms. So, and this normal form is really interesting for the analysis of return maps. And just to insist in the idea, the only point is just to do changes that don't destroy the possible orbit. The left and right system has the same structure, so we will pay attention only to the right part, for instance, and we'll suppress the superscript to alleviate notation, and the proof just proceeds by induction. We will details about just the first step, and the idea is to select for the initial system, select a change of variable, a near identity chain, which is polynomial. For instance, in this case, is the identity plus second degree terms. Note that the inverse change is not polynomial in general, and so you have a long expression here. But when you introduce this change, you will see that the linear part is respected, and we pay attention of the second degree terms, and just to insist in the only restriction we have, and we must respect the point of this line, x equal to 0, the y-axis, and then in the complex setting, you must respect this line, the y-axis. So for that, this change must have the factor z mass plus z bar. So when you put this condition here, you don't have total freedom in these three coefficients, but you must take coefficients respecting this equality. In fact, so you have only two degrees of freedom, to say that. Okay, we must substitute the change and the computation. Pay attention only on the terms of degree 2. You take this expression here. So if you select adequately these constants h20 and h02, you can remove this term and this one, and you get only this. The coefficients here is slave of the other two, so this term cannot be removed in general. So with this, we have got the second degree term just reduced to this term. Of course, with this change, you have changed all the other terms, but we will see now that putting attention to third degree terms here, you can also remove some. Here we obtain the general expression for this coefficient in terms of the expression in the original vector field. Then finish the proof for the first step. We simplify the degree 3 terms. Then the same procedure, doing the same procedure. So now you have this part fixed, and now pay attention to this, and you change this time. Well, we have renamed the variable to get the same setting as initial, and then now the to respect the points in the invariant line, we need all these four coefficients fulfill this condition. The computations are similar, and then you can reduce the degree 3 terms, all but one, by selecting these conditions. And so, you finally get the first step in the normal form. The remaining step is completely similar, so we don't need more details about it. What is a curious thing, and maybe I am not able to understand completely why when this happens so, is that in the case the gamma is different from zero, that is, if we exclude the center, the linear center situation, when the real part of the values is zero, then you can get another normal form in complex set, which is this one, and this is holomorphic normal form. This is not interesting for us because this, for us, the computation are more ordered in order to get the retropass, but maybe Gabriel or to obtain some ideas about this. Well, a lot of text here. Just is a computational remark because when you need to do the computations, the initial idea is just to reproduce the step you have done to get a normal form. But in every step, when you decided to do a change of variable, you must make the substitution, but you need also the inverse change to obtain the new vector field in the new variables. It's like when you change a matrix, you have the matrix, the pass matrix and the inverse, and following a clever suggestion by the book of Kuznetsov, you can avoid these inverse changes just by considering that you know a priori the normal form you will get, and just write the inverse change you need to get some degree in the normal form, put it here. This is the inverse change we have done in the proof of, which is put the old variable in terms of the new ones, and here introduce this factor which guarantees the invariance of every point of the continuous line, and then impose that the result is equivalent to the original one. So with this approach, you don't need to introduce for every change the inverse change, so it's much more direct in the computations. Okay. Now this part is standard because now what we want to do is to obtain the return maps, taking advantage of this normal form, and the idea is just to pass to the polar form. Here, as we have this vertical separation line, we introduce this polar transformation that is not the usual one, because x is r sinus and y is minus r cosinus. So this means that the angle the polar angle is has the origin in the lower part of the y-axis, and so these notations, we want to obtain the expression for the two return maps in here. The path to the polar form, thanks to the normal form we have obtained, is almost direct because you can predict the normal form completely, the polar form completely, without doing any calculations, because you have always this R2 R2K, and here R2K in every term, and this R expression here. We use the R and I for denoting the real part and the imaginary part of the coefficients in the normal form. Now the idea is just to integrate this polar form in the usual, just to integrate from 0 to pi in the right part, and from 0 to minus pi to obtain the inverse of the left. So this is just standard. We write the scalar differential equation associated to the polar form, and assuming these expansions, we have to compute these coefficients for every right, and using the initial conditions that the first one must be 1 and 0, and the other initial conditions must be 0. So we make the substitution, and weighting degree by degree in powers of R1, and this expression you get the first condition for the first coefficient, and here there are no subscripts or subscripts, are the same for every side. So the first is 1, and this is the condition for the second term, and so the solution for this is this term and the third term, and well, you can get as much terms in the expansion as you want, but the expressions are growing and growing. So we put here the results for the first coefficient, the left part, the right part, second, the third, and also the third only. Okay, we have the fourth. And in the case gamma 0, the computations are easier, as shown here. So with these computations, we can obtain the difference map, which allows us to study the stability of the origin just by putting here in the expansion the difference between these coefficients we have obtained before. And well, the first one coefficient, the variable coefficient, is just this expression. This expression is 0, can vanish only if these two focal factors, the sum is 0. This means that the origin should be with focus. If this coefficient is 0, the analysis is finished. We must not follow anymore. We can stop. So the interesting case should be this one. The idea is just to study the case in gamma minus is just minus gamma plus. This is the interesting case. And well, we record here that when this became 0 for all the term, and the first coefficient in this expansion of 0 is the coefficient of index p, we say that the origin is a quick focus term. Of course, if we have a pseudo center, then all these coefficients are zero, so that the different map is zero in an element theory. Then from now on, we only consider this the more interesting case, that is the FF system without focus. So we put here plus or minus gamma and the normal form for every case. Well, the computation now, when we put here the coefficient of the normal form, here are B1, B2, B3, B4. And in the case gamma equals to 0, the expression simplifies in a significant way. Here we put the 4 first coefficients, here only 3 because for our analysis the 4 will not be needed. Then we enter the final part of my talk. We work with the analysis of FF systems which are of linear type and quadratic. So this is the family of piecewise quadratic linear FF system without with focus. So we start with this form. This expression here is not in canonical form, but this is the canonical form we use for the linear systems, for the continuous linear system. And this is a linear situation, and we have the two parameters, B minus and other 2 here. So we have a problem with 5 parameters, the coefficient gamma and this force, the 4 parameters. The first point to remark is that when these 2 entries here are equal and the second ones are opposite, the above system is reversible. And then it's clear that the equilibrium point at the origin will be accepted. So in this case, all the expression for the decay should be 0. Okay. As we have done in the introduction, we pass to the general canonical form. And then, doing so, we obtain here a more involved expression in the second entry quadratic terms. We compute the normal form. It's not easy, even in this case, which is the simplest case. The expressions are a little bit involved, as you see. And for example, the 4 terms in the normal form have some polynomial here, the real part and the imaginary part, and these are these long expressions. Just in a quadratic case, it's really impressive. Then, to define the Jacob's constants, we must introduce some extra expressions to alleviate the notation after that. You see here some polynomials in gamma which are apart, multiplied by the exponential pi gamma, another 2 pi gamma exponentials, and so on. Then, when you compute the Jacob's constant for this case, you obtain, of course, the B1 0 was our hypothesis. B2, this expression with this delta, with involves the 4 parameters, the 5 parameters we have. And for the B3, and this is another expression. And in the case gamma different from 0, we also need the B4, which is this expression where this kappa is this expression involving the 5 parameters. So working with these results, we can analyze completely this family, obtaining in the case gamma different from 0, this step-by-step situation. When delta is different from 0, we have a good focus of order 2. If delta is 0 but rho is different from 0, we have a good focus of order 3. And if delta rho vanishes but kappa is different from 0, we have a weak focus of order 4. And finally, if these 3 expressions vanish simultaneously, and then the origin is a reversible pseudosensor. Because it's not simple, but you can show that if this situation appears, we have a plus equal to a minus and b plus equal to minus b minus. So we are in the reversible case. And for gamma equal to 0, the situation is simpler, as you see here. Then we only can have a weak focus of order 3, and we don't need to achieve the 4 coefficient, the 4 Lyapunov coefficient, because when these 2 expressions vanish, the origin is already a reversible pseudocenter. Okay. Well, now to finish my presentation, I repeat that in this work, the authors, Dennis, Braga, Jaume Libre, and Luis Fernando, show that when you have a discontinuous matching of 2 globally asymptotically stable, you can obtain a system which is not globally asymptotically stable. It's a recent work. So here we can give a result in the same spirit, but using local stability. So we show that combining 2 locally attractive weak focus, it is possible to get a repulsive weak focus. In fact, this comes in a natural way from the case gamma equal to 0 in our quadratic family, because working with this system, we can study every part as if it was extended to the whole plane, and we obtain that separately, forgetting this restriction, this system has a stable weak focus. In fact, a stable weak focus of order 3 is just the product of A minus B minus is positive, and the same for the right part. The two systems, when extended to the whole plane, should have a stable weak focus just with these conditions. Now, when you consider this continuous system, if you put this condition, but you force that this parameter A plus is greater than A minus, then we see with the previous proposition that the origin will be unstable weak focus of order 2. In short, when you merge 2 stable weak focus of order 3, you can get unstable weak focus of order 2. Okay, this is all. Thank you very much.
Questions, comments?
Yes, I understand that with this presentation, these normal forms, all becomes more natural, but finally you get awful expressions. But I remember we did with Tomeu and Rafael II, with too difficult, we took linear equations, but linear in classical linear, not x dot equal y minus f, y dot x on each side of the line. But I wonder, we want to characterize centers, and in this problem we found that if you put the line vertical or horizontal, one case is very easy and the other is very difficult. So maybe with your normal forms you can try. You fix the system, but there are two linear systems, but the classical linear, not the easiest one, only, and then you put the line vertical or horizontal. I mean, one case is easy and the other is impossible for the moment. So maybe with this approach,
It's a good idea to consider this case.
yes, because it's very minimal in parameters, so maybe these normal forms. So, okay.
Well, you can give the reference for
Yes. Yeah.
Thank you.
Thank you. More questions? One more question. Let's thanks again. Now we have the poster section.
Good morning, everyone. It's a pleasure to present the next speaker, Professor Antonio Pinto de Carvalho, which is from Universidad Federal de Minas Gerais. Her talk is about billiards in the sky.
I will not take the risk to translate Guimarães Anyway, I'm here in the name of the Grupo de Sistemas Dinâmicos from FMG to congratulate Mark Antônio for the 80 anos que ele vida toda pelo emérito. And let's prepare the match 90. So I'm going to talk about the title billiards.
Sonia, the microphone is not working.
Assim, escuta.
Pouco melhor.
Ficou melhor? Então tá ótimo. And as I see, there are perhaps one billiard player here in the audience. So I'm not going to talk about the last theorems our group has, but make a little marketing about how beautiful billiards are and how useful billiards. For those that do not know what a billiard is, the problem consists, it's exactly what it is. You have a particle that travels with free motion in a table and makes elastic collision with the boundary. But the table do not need to be rectangular. So we decided to work with oval tables. So we don't have pockets and we model it, we can model it two ways. We can think about Hamiltonian, which is the kinetic energy and a zero infinity potential, zero in the table, infinity in the boundary, or as a discrete dynamical system in the following way. If you have a collision in the direction of motion, the next collision in the next direction, since it makes equal angles, are well specified. So we have, if you parameterize the boundary, something, for instance, parameter, and take an angle, for instance, with the tangent. So to reposition direction, we have the next position direction. So we have a function from a cylinder, an open cylinder. So if the boundary, as we work, is an oval, the oval is what we imagine. A simple closed curve, regular, is strictly positive curvature. The billiard map, if the oval is CK, the billiard map will be a diffeomorphism, CK minus 1, because we need the tangent to calculate the direction. So we lose one derivative. It is conservative, it preserves volume, it's reversible, if you follow a trajectory and you follow the reverse trajectory, you have the inverse billiard map. So it's reversible. You can show that it is a twist map in the sense that it's almost Hamiltonian. If you take the distance between two impacts, you have the canonical formula. So the arc length parameter and cosinus theta are canonically conjugate variables. So this is a very special, discrete dimensions dynamical system. It has some general properties. For instance, if the oval is at least C2, you have periodic orbits of any period greater than 2, because a billiard do not have fixed points. And this is a Birkhoff, 1927. If the boundary, the oval, is at least CK, you have invariant graphs near the boundaries of the cylinder, of the phase space, if you prefer. And this is a result. But Lazutkin with a bigger differentiability, and Raphael Duarte in 1982. And it has some generic properties. And generic here, we cannot perturb a billiard map as a diffeomorph, because it will not be a billiard anymore. So what we have to do is to perturb the boundary to be sure that we stay in the billiard world. But with this kind of perturbation, we can prove that it has only a finite number of any periodic orbits for each fixed period. At least one of them is hyperbolic. This is a C2 property. For any hyperbolic periodic orbits, the invariant curves either do not meet or meet transversally. This is also C2. The two periodic orbits have islands, and as we use the Birkhoff normal form, we need the C5. And but this is a result of our group in 2003 to 2007. And all elliptic orbits have islands. Is a result of Bunimovich and Grigo from 2010. Xie and Zhang, for C-infinity boundaries, prove that for the same point, the stable and unstable curves always meet. And Tere is there now. Tere is working with analytic boundaries and using it, improving this result without using numerical standards. But here we use this. But the table need not to be flat. So what we do? We take a surface, a Riemannian surface, complete. we take a neighborhood where 2 points are connected by a geodesic inside this neighborhood. So there we can take a curve, an oval, and now we ask that the geodesic curvature is positive, and now we can play billiards in any surface. And of course the billiard trajectories will follow the geodesics and then make equal angles when hitting the ball. And the same properties we have for the plane works well here. It's a CK-1 diffeomorphism, it's conservative, it's reversible, it's a twist map, so it has orbits of any period, it has a generating function. There is the geodesic distance between the two impacts. And this was proven in the case of surface of constant curvature by Luciano, that was one of students, and in the general case by Cassio. This is another of our students. Well, once you know what billiards are, let's go. Let's look a little at these guys. So when I was at Toulouse, once I was in the printing shop, just trying to print a poster for the Congress about billiards, generic billiards with a big picture. And the guy that was next to me told me, oh, my supervisor has the same picture. And he was an astrophysics. So I went there to see what the astrophysics were doing. And it was Ligneres, she was a supervisor. And they were looking at acoustic modes in rapidly rotating stars. What happens is, when a star rotates, it deforms in the equator and becomes an ovoid, symmetrical, symmetries. And the interior of the star is not, it's an isotropic medium, meaning that the interior is not homogeneous. So how did they look at those acoustic rays? They look at them as optical rays in isotropic two-dimensional medium. Because of their rotation, you can stay, you cut by the rotation, and then you are in the plane, and inside of it, the optical rays will follow from halos. And they simulated it and had this beautiful picture. And they say that they said they could see elliptic islands corresponding to the regular motions, and then a kind of chaotic sea that will enable us them to understand why the star pulsates. So this is my picture, and this is their pictures. I said, well, we know how to do this. And what we do, we put polar coordinates, we put a medium index that depends only on the distance to the center of the star. We construct the optical Lagrangian, and then we know that the geodesics or the optical rays will be the solutions of the Euler Lagrangian equations. Or if you want, you put a Riemannian metric that is simpler. And then And the solutions, the optical rays, will be the geodesics of this metric. And now you can build a billion map in this new context. And if you parameterize the boundary by Ample's parameter, for instance, you decide what the angle is, and then you build a map, an optical billion map that will be reversible, conservative, Cj minus 1 if the boundary is Cj, and has its twists, so has periods of periodic orbits of any period. Generically, you have at least one unstable, and we'll have invariant graphs near the boundaries. This is an unpublished work. And what we are trying to do now is, what can we say generically on the medium that guarantees that, at least for this symmetric oval, we have the generic picture that they show. Changing a little bit, but still in the sky. In 1949, Fermi asked if the pulsating magnetic field of the sun could accelerate a cosmic ray in order to enable it to reach the Earth. And the first toy model trying to understand this problem was the Fermi model, that you suppose that you have two walls, one is fixed, the other is moving, and you have a ball that bounces from one to the other, and there are some, Duadji, for instance, proves that if the moving boundary is periodic or quasi-periodic, then you cannot accelerate the particle. You cannot have an infinite gain. So inspired by that, we said that the magnetic field of the sun is not a wall. So we began to think on a moving boundary and a billiard inside this moving boundary, and asked, can we give can the energy of a particle go to infinity? But the problem here is that you need 4 variables to understand the problem. You must know the time to see where, in which boundary you are hitting. Then you hit where in this boundary you are hitting. Then you must know the velocity you arrive, the speed, the modulus of the velocity, and the angle. Because if the boundary is coming, it will increase the speed. If it's going, it will diminish this, and the angle will change. So we need 4 variables to understand this problem, and we have to eliminate some very singular case. For instance, the particle comes, hits the boundary, and then becomes this 0 velocity. Or it comes and tangentiates the boundary. So we have some singular case that have measure 0, so we are not. So what we can show is that these are old results. If you take when, where, speed, and angle, the next, this is the condition to avoid the singularities. The next, when, where, velocity, speed, and angle are well defined. What's the problem here? The problem here is that we have a four-dimensional diffeomorphism. And we lose two derivatives because we have to take in account the velocity of the boundary and the angle with the tangent. And we know how to prove it. That is ck minus 2 diffeomorphisms. And we have some results. We know that if in the rigid case you have a stable two periodic orbit, the movement of the boundary can turn it to unstable. If you are in the case of the breathing circle, you fix the center and then you breathe. You cannot, you will always have bounded gain of energy for a trajectory. And numerically, this seems true for elliptical. And from 1995 till now, there are many analytical and numerical studies done by many people with standard and billions, but we don't know if there is a movement that enables infinite gain of energy. Well, one more example, which it's a problem that was worked by Bartello, De Blasi, De Hacini, and they studied galaxies with a black hole inside. And you imagine you have a particle inside that galaxy, so it will travel in a Keplerian hyperbola inside the galaxy. Will go out making a Snell refraction, and then the galaxy will attract the particle again. So you have a harmonic ellipse. And this, as it goes out and then come back inside and then it goes out again, they can define a billiard in the following sense. If you go out from a certain point of the boundary with an angle alpha 0, you take the ellipse, you will come back to the galaxy, you will enter, you take the hyperbola, and then you go out again. And so you can make a billiard that takes a point and an angle to the next impact with the boundary and the angle. And they proved that if the boundary of the galaxy is a circle, this billiard is integrable in the sense that if you go out with an angle, you will go out again with the same angle. If the boundary is sufficiently close to a circle, then this map is a twist map. You have all the good properties of twist maps. For instance, any number of any periodic orbits of any period, for instance, and quasi-periodic orbits. And they have a simulation of an elliptic boundary where they see the generic feature we see for the plane case. You have islands and then an apparently chaotic sea surrounding these islands. And those are results of De Blasi and De Hacini, 2022. And finally, I said 4. Bulletin in 2016 was interested in anybody problem. But he was interested in the near collision trajectories, periodic near collision trajectories. There are trajectories that comes near to a collision and then go near to another collision and then near to another collision and then come back periodically to the same situation. And what he proved, if you can, this can be modeled. Now you take the kinetic energy and the potential that will be singular in the surfaces for manifolds of collision. And he notices that when you make when you take the limits, he says that a near collision arrives close, order of close to the collision. So if you take mu to 0, you see something that's not exactly a billiard, but it's a degenerate billiard, in the sense that if you have the collision scatters, they have collimation greater than 1. So you can imagine you have a curve in R3, you hit that curve with an angle, and the next angle is not totally defined, in the sense that you have a cone of possibilities to go out. So you have to define how you go out. And then what he shows that you must preserve the Hamiltonian, you must preserve the energy. So you come with the trajectories of the n-bar problem, you hit the scatterer, you preserve the energy, so you choose the way to go out that preserves the value of the energy. And then you go to the next sketch, and then you go, and then you go, and then you go. What he proves is that, he calls it the collision chain, when you go from one scatterer to the other, from. And what he proves is that if you have a non-degenerate periodic collision chain for the degenerate billiard, it is shadowed by a real orbit, periodic near collision orbits of the system. And that's all. And thank you.
Thank you so much, Sonia. It was a very interesting topic. We have time for 1 or 2 questions.
Sonia, in the optical billiard, I did not understand one thing. If you start with the initial condition inside, are you sure that it will hit the boundary?
Yes, because the million index only depends on the distance to the center. I put the center inside of the table. No. The center of the star is inside the table. And you put the million index, some function that depends only on this distance, and then you don't have
Closed ray inside.
no.
Another question. When you
But
have,
you can do it, or you can say, I will choose only.
Another question, when you have the galaxy, you said you have this Snell law when you cross from inside to outside the galaxy, but why?
Because it goes out. That's that's how they did it. And I don't know. I don't know if it's a astrophysical fact or if it was a technical fact. Should ask my husband. He's an astrophysicist.
More question?
I have a question.
I
have a question. Maybe a curiosity. You started with the billiard, and then you show the situation inside of a star, then you go to the galaxy. So I was wondering if there is any more cosmic objects that could be modeled by billiards, or if you know any. The next step.
No. Because what we are really working now, is on. There are many questions. One is what kind of surface can we take to get what can we say about the surface to guarantee you have a generic opinion? There are some very, very strange things that happens. For instance, a geodesic circular billiard is always integrable, except in some surfaces where it's not. So now we are trying to understand not only the boundary of the billiard, but also the geodesics that the billiard forms. No, this was marketing.
It worked.
It worked.
More question? More question? Let's send the speaker again. The next speaker is Douglas Park. Okay, let's start with the next speaker, Douglas Coates. He's from Universidade de São Paulo. His talk is about natural measure in statistical property for non-statistical dynamical systems. Thank you.
Thank you very much. Thank you very much to the organisers. I think it'll be hard to hold them. If anyone can't hear me, I will talk louder. So thank you very much to the organisers for the invitation. It's a pleasure to be here. I think my topic is maybe slightly further away from a lot of the topics in this conference, so I'll try and give a bit of an introduction to the area. So today I'm going to talk to you about a family of maps of the unit interval. So I'm going to be interested in discrete dynamical systems, maps of the unit interval, and I'm going to be interested in a particular family of these maps that were so-called Thaler maps. So these are maps that were introduced by Thaler in the 80s, and they are particularly nice because they exhibit a very rich dynamics, but they're very simple. In fact, they're one of the simplest models of non-uniform hyperbolic dynamical systems that we can have. So I will start by telling you what these maps look like. Well, I'll draw a picture first, and then I'll give you the conditions. The maps are maps from the intervals themselves, and they have some finite number of full branches. In my talk, I'm going to let little d in a number of full branches. Okay, and these maps are uniformly expanding. The derivative is strictly larger than 1 everywhere, apart from at the fixed point inside each branch. Okay, so in each one of these branches I have a fixed point, and at this fixed point my map makes a tangency to the identity. So let me be a little bit more formal. So I'm going to assume that my maps F, there is a D bigger than 2, subintervals I1 to ID, that partition the full unit interval, and I want my restriction F to one of these little intervals. I want the image to be the full interval, and I want this to be a C2 diffeomorphism. Orientation preserving diffeomorphism. Okay, that's my first condition. My second condition. Oh, sorry, I want to say something else. I also want these maps to have bounded distortion. So I want these maps to these diffeomorphisms to have bounded distortion. So if you're not sure what this is just some technical condition. I assume the second derivative over the square of the first derivative to be uniformly bounded. Can everyone, is it large enough, the writing? Is it all good? My second condition, like I said, the derivative is strictly larger than 1 for all x which is not one of the fixed points. The fixed points I will label by xi1 to xid. These are my fixed points. And I want the derivative at these fixed points to be exactly 1. Final condition, which is going to allow me to say some more specific things, is I'm going to assume that these maps have a nice expansion near the fixed point. I'm going to assume that it's a nice polynomial expansion near the fixed point. So near each fixed point, there exists an alpha, positive. There exists a C1, let's see, B1 to BD, positive, such that near each fixed point, my map is asymptotic to the polynomial Bix minus xi I to the 1 plus 1 over alpha. Okay? So I'm just assuming that near each fixed point is a polynomial of order bigger than 1. Alpha I is just some positive parameter. It turns out that it's convenient to parameterize by 1 over alpha instead of alpha. Alpha, sorry. So for this talk, I want to focus on the case that this alpha is the same for every fixed point. And somehow, if you have different alphas, they always reduce to a case where it's just what is important is the number of fixed points with the same alpha. So it's anyway. So now we're just going to fix. We're assuming the tangency is the same at all of these points. And we want to understand the statistical properties of these maps, the ergodic properties of these maps. So the natural question is whether these maps preserve a invariant measure, an ergodic invariant measure, and this was a result of Thaler's in the 80s. A series of papers in the early 80s. And he says that there exists a unique measure mu, which is absolutely continuous with respect to the vector, sigma finite, which is ergodic and F invariant. So these maps always preserve a sigma finite, ergodic, absolutely continuous measure. However, this measure is not always finite. You can't always normalize it to a finite measure. Okay, so the second part of this result says that this measure gives finite mass to the interval if and only if this parameter alpha, I always get this the wrong way around, is bigger than 1. Okay? So this measure is still ergodic in this case, but we don't have the ergodic theory. So for those of you that are not familiar with infinite ergodic theory, my definition of ergodicity is that invariant sets, so if a set is invariant, then either this set has measure 0 or its complement has measure 0. Okay, so this is my definition of infinite measures. And in this case where alpha is bigger than 1, the ergodic theorem tells. Yes?
What is the condition on the left-hand side? Is the measure is finite?
I can't, sorry.
What is the condition on the left-hand side?
On the right-hand side is, sorry, this is, let's say, this is less than infinity if and only if alpha is bigger than 1.
Thank you.
So, thank you. So, in the case where alpha is bigger than 1, a lot is known about these systems, but the focus of my talk today is going to be on this infinite measure. So I'm going to assume that alpha is less than or equal. Okay? So, in this case, as I said, the ergodic theorem fails in the following sense. So, Birkhoff sum of any observable goes to 0. So this is not very useful. But you can still have possibly physical measures. So let me say a little bit about what physical measures are. There might be some other measure that describes our dynamics. Okay, so this is going to be the main object of the talk. So I'm going to take a point x inside 0, 1, and I'm going to define En of x to be a probability measure defined by uniformly distributing mass on the first n iterates of x. So I take my orbit up to time n and I uniformly distribute mass along the first n iterates of this. If this sequence has some limit, then that limit somehow is the limiting distribution of this x. It describes the statistics of the orbit of this x. It tells you exactly by definition how the orbit of x is distributed in space.
Oh, sorry, Douglas, I don't understand. You wrote assume alpha less or equal than 0. You say that it's an implication of that assumption.
This is a consequence of having. This is what the ergodic theorem says when your invariant measure gives infinite mass to the whole system. So.
Thank you.
So I'm going to be interested, so let me say, so the definition, measure is physical if the Lebesgue measure, the set of x, so measure nu is physical if the Lebesgue measure is set of x such that En of x converges to nu is positive. So I said if this sequence converges to something, that limiting measure describes the distribution of that x. The physical measure is one that describes the limiting distribution of a lot of x, a positive Lebesgue measure set of initial conditions. Okay, so these are good measures. So for example, any SRB measure is physical, any finite absolutely continuous invariant measure is physical, but in this case we don't know. Okay? So, what I will say now is present some recent works about the behavior of the Zn, and everything I'm going to say is going to be joint work with Ian Melbourne from the University of Warwick and Amin Talebi from Tehran. Okay? So our first theorem is that there are no physical measures. Okay, that everything is, in this situation, everything is very badly behaved. And what's more than that, in particular, if I let S be the set of all convex combinations of the Dirac masses of the fixed points, so I take my fixed points, I look at the set of all convex combinations of the Dirac masses of these fixed points, then the set of limit points of En of x is equal to this simplex of almost every x. So this is telling us not only that these empirical measures are not converging, but they're accumulating in some non-trivial objects. They have a lot of limit points. Let me give you just a bit of very heuristic justification as why that is. If you haven't seen these intermittent maps before. So what's happening here is that if I zoom in on one of my fixed points, every time an orbit gets sent close to this fixed point, the derivative here is 1. So it's going to spend a very long time near this fixed point before it escapes. Okay? And what this result is telling us is that we're not accumulating at any one of them in particular. The set of limiting distributions is somehow evenly spread amongst all of these fixed points. Okay, but not evenly spread in the sense that there's some fixed proportion of time that we spend at each one. It's not converging, but it's accumulating at every convex combination of all. Okay, so let me rewrite this object En of x. This was this measure. Now I can write this as just being the averages of the push forwards of the Dirac masses at x. And we know that this is not convergent. So a natural question is what happens when I replace this singular measure with something that is that it has a density. What happens when we replace delta x with a measure with a density? Okay, we replace it with something that isn't non-singular. Okay, and the answer is that we do get convergence. So 1 over n sum k, there exists some measure nu that lies in this set of special measures such that 1 over n sum k 0 n minus 1 f sum k lambda converges to the measure. Okay, so this is saying that if we, instead of considering a fixed initial condition, if we average over them, we do get convergence, and this convergence happens for every initial distribution that we choose. Okay, and moreover, we show that it's not necessary to take the Cesaro average. It's that this, just the push forwards of every probability measure is converging to this specific measure. Okay, so so we've seen this. So this is a little sketch of what's going on. So we have a space of probability measures. Somewhere inside this space there is a convex subset that I call S. This was the set of all convex combinations of the Dirac masses at the fixed points. And if I take a typical En of x, it's moving around this space and it's accumulating exactly on this segment. This last result is telling us that there is some special measure inside here where this distribution is concentrated. Okay, and you can make this formal in some way. The thing I'd like to finish off with is to give a corollary to this sort of result. So this situation you call new and natural measure. So why would this be interesting? Is what does this measure nu tell us about the system? Is one thing it tells you is it gives you a decay of correlations. So one thing that we can use this sort of theorem for is to prove the following sort of result. If I take two real valued functions, phi here to be 1, so it to be L infinity, and continuous fixed points. Then we have a decay of correlations in the sense that this And I think I will stop there. So that's the last thing I want to say.
Thank you very much, Douglas. We have time for some questions.
Hi, can you also obtain some results for CLT or North Standard CLT for this type of map?
So in this case, you definitely don't have any central limit theorem. So you have no central limit theorem at all. What is replaced is you have a limit theorem for these objects. So these objects do satisfy a sort of central limit theorem in the sense that you can describe exactly how they're distributed in this space. And it follows an arc sign.
I have a question. So this limit measure, nu, depends on what? Because it's,
So this measure nu is, you can determine exactly what it is. If you know the map, then you can determine what this is. So this is a convex combination of the Dirac masses at the fixed points, and you need to know what those weights are. And these weights are, there's some formula for them, and the things that formula depends on is about the second derivative of maps as they approach here and what happens at the discontinuity. But they're all things that you can calculate.
More questions? No questions? Let's speak again. Let's